Hello, I'm Matej Marquez and I'm a senior researcher and project leader in the New Media Art Institute of Creative Technologies of the University of Mons in Belgium. Today I will talk about AI and creativity, and this talk is intended to be very general and not very technical. And that's why actually even the references are not necessarily scholar papers, but most of them are links to vulgarization websites, etc., so that most of the people can get something from this talk, hopefully. Okay, so this talk will be structured around three axes. So first of all, I will give some examples from different domains. Then I'll go through some architectures, deep learning architectures for creativity. And finally, we'll ask ourselves the question of how creative is AI? Can it replace humans or not? Well, and this is the first part about artificial creativity examples. So I begin with this automata of Jacques-Droz, which was done in 1770. And still working today. You can visit it in Switzerland, in Neuchâtel, in a museum, and you can see a musician in the middle, a draughtsman on the left, and a writer on the right, and they all can be programmed to do something different. And this is really very impressive for the time. Much later, in the 50s, you have the mathematics of Jean Tinguely, which are machines. So here you have just a number 9 and number 10, for example, mechanical machines, which will draw some specific path on a paper. And this path will, of course, depend on the mechanics of the machine. Here around early 2000, Léonel Murat made some swarm paintings. So swarm paintings were really based on artificial intelligence. The idea is it uses ant swarm algorithm with some autonomous systems which model ants and their cooperation and coevolution. And actually all this autonomous life which is happening into the algorithm is then painted on a paper based on this weird printer here. Also, in terms of robotics, you have this robot lab robot here, which in 2014 generated a painting, a drawing actually, with a single uninterrupted line and 900 million movements. And that's a painting from a view of Mars. And last year, here comes the Shimon robot that you have the reference in there. This is a very interesting setup because the robot is working together with humans. Okay, so it's a musician robot. The robot is able to compose lyrics from text databases, to propose lyrics, and humans can cooperate. They can say, okay, that lyrics is this text is good, that one is not. I'll keep that one or not. The robot will also propose melodies and pieces of sound, etc., that humans can work with that. The robot will play them, so you see that here it has a mechanical system to play it on this instrument, and it sings the song and also move the head in a choreographic way depending on the sound and on the person around. So it's really a collaborative robot based on deep learning and artificial intelligence. It's very advanced. And by the way, at the end of the talk, I will put maybe 1 or 2 minutes of the first song, which was made with this robot. Okay, so after robotics, let's dig a little bit into the text. Here with Shakespeare text datasets to generate Shakespeare-like text. generating informatic code from a dataset from the Linux code source, and generate here a full novel written by an AI based on a novel text. So in all those applications, the generation is not bad in terms of style. So here you have real Shakespeare-like text, real C-like code, and real novel-like structures. But the general meaning is not necessarily very interesting. So here you can see that it's quite weird. Well, let's talk about sound now. So there is first this attempt of finishing a Beethoven symphony by using data from the beginning of the symphony and from other symphonies from Beethoven, or even from artists that inspired Beethoven, to have a quite broad data set. And the idea is to finish this symphony in a way that people think that Beethoven made it. Another attempt here is of Alex da Kid, who used the IBM Watson AI modules to generate first text. So from data sets of text linked with emotions, it will generate possibilities of text, and then the artist will choose the best one. And that's the same for audio. From a lot of audio data sets, several themes are generated, and the artist chooses the best one. And all those approaches give quite good results when the artist is also involved into the creative process. Okay, so let's talk about food. So here it's about beverage. In 2019, there was this AI whiskey, which was so the idea was already to sell it. So I didn't check if they really sold it and if you can still buy it. But the idea is that they use the Microsoft Azure AI platform to to make a new recipe, actually a new whiskey recipe from a data set of a lot of whiskey recipes, including award-winning recipes. Okay, so that's quite interesting. Another approach, which is a little bit older here, is also interesting because you just show an image of food to a camera, and the AI will be able to segment what you have in your image, recognize what you have in your image, and from there it can propose either recipes which are close to the one that you have, or even nutrition facts, etc. And now concerning body, you have Wayne McGregor, who is a famous choreographer, who provided his database of video dance to an AI which analyzed all the poses of the dancers and is able to suggest, actually even in real time, new and sometimes original ideas of movements that the choreographer can choose or not. Then you have Anouk Wieprecht, who transformed fashion actually by adding a lot of sensors, like in here, and providing possibilities of interaction and much more than just simple fashion. And after the body, we go inside the body, and we go here into drug synthesis, so what we call the novel drugs. And here you have references, and this is very interesting because they use artificial intelligence, maybe initially made for text grammar and text generation, and they are adapted for generating shapes, very different shapes of molecules which can fit in specific active sites. And so they propose combinations of molecules, and they propose also to make very rapidly tests of virtual tests of those molecules. And this is very, very interesting, especially in situation as we have now, and when we can see that we can have a vaccine which is very, very fast compared to what the time that a vaccine should take normally. So in design also, you can synthesize based on AI almost whatever you want in terms of design. So on the left here we have this shoes generator. So you have the paper in there from 2017. Yeah, you can even see that the shoes are better and better at each new iteration of the algorithm. You have also this idea of building chairs. So the question was, we want like beautiful chairs, or at least useful chairs, with a minimum of material. Okay, so that it's cheaper and more ecological. And you give those constraints to an AI, and you have this kind of result at the end. Again, that one was done with cooperation of designers, which were part of the loop. Concerning gaming, deep learning is a real revolution, especially when coupled with reinforcement learning. So as you can see here, in 24 hours of learning, AlphaZero, that you probably know, the algorithm AlphaZero, had a superhuman level in several games, actually, in chess, in shogi, and in Go, of course. And it defeated a world champion in each of those categories. So this is really, really impressive, and it's such impressive that actually one of the Go champions just quits because he said AI cannot be defeated. But simulation is not about game only, it's also about much more. So you can have simulation for training, for example. So that's the case here, where last year you have an algorithm which beats F-16 professional pilots in a dogfight. So a dogfight is a fight where the planes are very close, and so they need to move a lot around to avoid being destroyed. And what they say that employing AI here will make pilots more aware of how they can and should think differently while up in the air. Okay, because the machine found some kind of approaches which were very weird, and that's why the human pilot was beaten in there. So in the image domain now, so most of you probably already know Deep Dreams. So here we have an application which is called Dreamscope, which is quite easy to use. And the idea is that you provide an input, which I mean could be just noise, but it can be an image like a starship in here. And then depending on the number of iteration that you use, you will have some filters of the deep neural network which will respond, and those filters depend on how they were trained, for example, the datasets they were trained on. And if you take general datasets, you will have a lot of filters with like animals, faces, eyes, and things like that, which will appear on your image. And the more iteration you do, the more weird things appear in your image. And yeah, you have this artificial piece of art, let's say, which was done here by an algorithm, and that one was sold more than 400,000 dollars. So you have the price here, $432,500, which is an amazing price for this artwork. So I just let you to be judge if it's worthy. That's another question. But I mean, there are people who paid a lot for that, like the first expensive artwork, artificial artwork. And finally, for images, another very well-known creative approach is image style transfer. So the idea is quite simple. You have an initial image like that one. You have a style that you want to use, for example, some Van Gogh here, or that one, or that one. And the idea is that the model will take the style from this image and put it on this image, and you will have a kind of Van Gogh car here, or each time you have the initial image and the style transfer on the right. So you see that that's quite convincing. That's really interesting. Okay, so after a tour of examples in artificial creativity, let's talk a little bit about the deep learning architecture which make those examples possible. First, we'll talk about a specific architecture which is called CNN, like convolutional neural network, which is mainly used for images. So you have images here from a Stanford course on that. So how does it work? So you have an image, the input image here. Then you have an encoder, which will basically extract features. Okay, and those features are three types. If you take low-level features here in the first layers, you will have colors and edges and simple features. If you go in the middle layers here, you will get mid-level features, which are more complex. And if you go in the last layers here, you will get high-level features, which are even more complex, like wheels, eyes, windows, whatever, something bigger. Okay, and after that, you add a trainable classifier here to be able to have classes about what you find in the image. So here saying, okay, in this image I have a car, and here I have a letter, and which letter, etc. Okay, so to summarize, it's really simple. Finally, you have a feature extractor extracting low-level, mid-level, and high-level features, a lot of features, millions of features. And then you have this trainable classifier, which will provide you which class you have in the image. But this is not usable as is for creativity applications. That's why we'll see in the next slide how to make it more efficient for that. For image style transfer, for example, that we saw an example in the previous slides, it uses CNNs or encoders, actually CNN encoders, in a simple way. So you have a content image here, a style image. So you want to extract the style from here and to add the style to this image in order to generate the image here. So the output is the third image which will be generated. Then you have three CNNs, three encoders, one which has as input the content image, one which has as input the style image, and one which has as input the generated image. And then you have two losses, a content loss where you actually compare the last layers of your encoders from the content image and from the generated image, ensuring that the high level structures are quite similar between your generated image and the content image, because you want to keep the image structure. And on the other side, you get style loss to have some similarity between the style, even at low level features, mid level and high level features. together to have a similar style between the two images. Okay, so you have two different losses, you combine them and you generate some image by that. And of course you do that several times until you have something convincing at the end. In addition to classical CNNs, we have another architecture which is called autoencoder. So basically an autoencoder is quite simple. You have an image, you have an encoder, which is the first part of a CNN actually, the convolutional part, the feature extractor, and then you have a latent vector, which will be a kind of compression of this image with the most representative features. And on the second part, you have a decoder, which is doing deconvolutions and will lead to an image. Okay, so you have an image which is encoded into a latent vector, and this latent vector can be decoded to another image. So to have a better idea about what you have inside, is that if you take a face and an encoder, in the latent attributes can be related to the face, so about smile, skin tone, gender, etc., etc. So you don't know what this means at the beginning, but by using differences with the image after decoding, then you can try to understand what the latent attributes mean. And to go further, we can get a variational autoencoder. So it's not a big difference actually. You still have an image, an encoder, a latent vector, a decoder, and a final image. But here you have an additional step where you can compute the mean vector and the standard deviation vector, which will give you basically, I mean, you also need to change the loss, but that's, I will not go into details here. So basically what you have is that the latent vector is can be a space where you can much more easily choose where you are in this space. So for example, you have for the smile, you will have a probability distribution, for the skin tone also, etc. So you can go and pick up different values in here, and if you can pick up different values in here, the interesting thing is that the decoder will synthesize an image which might be different from the initial image, but where you can yourself change the different latent attributes here. And this is very, very interesting. So in this paper, we have an example of original images which were provided to the autoencoders. And here, just by playing with attributes in the latent space, you can change a lot of things in a very natural way. For example, here you change the sex from woman to man, from man to woman, woman to man again, etc. Or you can add glasses, or you can open the eyes, you can shut the mouth, or you can change the age. So here you have people which are much older than in the original images. And of course, you can mix all those attributes, and this is really a very interesting result. Okay, another architecture, in addition to autoencoders, is about the GAN. So GAN is a generative adversarial network. So what does it mean? So you have adversarial networks. So it means that you have two networks which fight, let's say, one with the other. So typically you have this architecture in here. You have a generator, a network which generates an image. So for example, an image like that. And on the other side, you have real images, and you have the second network, which is a discriminator. So the discriminator will just tell you if the image comes from here, which means that that's a fake image, or if the image comes from here, which means that that's a real image. Okay, so the purpose of each network is different. So the generator network will try to fool the discriminator by doing as well as the real images. And the discriminator will try a lot to be able to discriminate between real images and synthesized images. Okay, and by this competition between the two networks, you can really get very interesting results. So what you will have is that you will have better and better synthesized images, okay, and you have a better and better discriminator at the end. So you have two examples here. I mean, there are much more. So here on the left, you have the real flowers, okay, from the data set. And on the right, you have synthesized flowers. So you see that if you look at them, at least for far from the flowers, they look plausible, at least natural. So that's not necessarily an issue. You're not surprised by this kind of flowers. Here you have airplane wings shape propositions. So you have a lot of propositions for that. So you can synthesize images which are close to reality, but however, which are different. So that having this difference introduce here the creativity of the network, actually. Okay, and the last architecture we'll talk about is reinforcement learning, which is actually modeling how real humans learn in real life. Well, we have a brain and we do some actions on our world, and then we get a reward, so which might be good or bad depending on how good are our actions or not. That's the same for the algorithm, actually. For example, the algorithm will try to make a move and get feedback like you win, you lose, or something like that. And then it can learn and get better at each iteration. It will need a lot of iterations to be good, but at the end it will be really good. So of course this is used in gaming and simulations because you need to do wrong things and just get the wrong reward, saying that's the wrong thing, but without destroying something, crashing a car or exploding something. Okay, so that's why it really works on simulations and not in real life. So here you have this paper on Atari games, which is really amazing, where the model has no idea about the rules of the games, Atari games. It will just see the pixels as like we have a webcam looking to the screen and getting the pixels. And then the algorithm will try to see what happens. Okay, if I go right, if I go left, do I win, do I lose, etc. And all those feedback will make it be better and better in just a few hours of simulation. So the interesting thing is also that the algorithm can adapt to a lot of different games just based on pixels. So it only has what a human would have by playing to a new game, and it's really interesting. Okay, and now we are at the final part of our talk, which is more philosophical about how creative is AI. We saw examples of that and architectures, and the question is AI capable of replacing humans, for example, in terms of creativity? Okay, so as we want to go more into the conceptual part of the creativity, we need a basic definition. So a creative idea is actually novel, at least on some domain, which can be different from the first domain it was applied, and valuable in practice. But of course, something beautiful is always valuable also. Okay, so not necessarily only practical, but also aesthetics is interesting. So about the creative process, we have a problem and we want a creative solution. And then we have this conceptual space, which is defined by a search space, so something that I need to dig in to find the solution, and of course the boundary of this search space. So how to expand this process of creative ideas? Well, there are several ways to do that. So first you have exploration and combination. Okay, so exploration means that you want to explore in order to find new ideas. Combination means that there are already existing ideas, so nothing new in there, but if you combine them, you have something new. Okay, so you can generate something new. And then you can transform the conceptual space, so you can transform the search space or the boundary space here. And that can be done in two ways, either by convergence, which means that I'm trying to find the optimal solution of my search space in order to find the most creative solution, or the other way around, by divergence. I want to enlarge and the search to different solutions, and maybe they try to find another one which might be more creative. Okay, so you have these two movements of divergence and convergence, okay, and exploration and combination. So concerning the current techniques, especially deep learning, they are based on optimization, actually. Okay, so on a loss function optimization to search the best solution. So they will be very good in space transformation based on convergence toward the best solution. And also they will be able to do combinational creativity, especially if the domains or the training data are not too far one from the others. Okay, so deep learning will be good in space transformation based on convergence and combinational creativity. On the other side, it will be very bad in divergence, which is very difficult to reach, in boundary transformation where humans are needed, or in exploration where maybe just random or gradient search can help in that. Another important point is the data. Deep learning really needs a lot of labeled data. And if you have that, you can do a lot of very interesting things. But if you have a domain where you don't have enough data, or the data is not labeled, or you have rare events which are interesting, this is very difficult to handle by deep learning. And finally, to finish this part, we will talk about types of creativity. So here you have mini C and little c, which is about everyday life creativity. Pro C, which is what a professional would do in a creative way, which is a good result, but without a revolution in there. And big C is disruptive creativity. Okay, so the huge majority of example that we saw are mini C and little c. Just two of them, in my opinion, are pro C. It's about the novel drugs, synthesizing drugs, because they use sometimes algorithm from text, for example, to apply them to molecules, so which are very different domains. So this is very creative. And all these reinforcement learning models in gaming and simulation, which are able to find solutions that humans don't think to, because there are a lot of parameters and they can find new solutions in there. So this is Pro C. And in my opinion, that's very personal, I think that there is no big C for the moment in AI. First, because we need more multimodal approaches, as we humans do. Actually, we have a lot of data sets in our brains, not just one. and also meta models. And for the moment, they are all designed by humans. And finally, there is this big issue in here that we talked about. Deep learning is about optimization. It's good in convergence, but very bad in divergence. And sometimes disruptive creativity is very divergent and especially suboptimal. Okay, so you just have a kind of feeling that something could be good, but you have no proof that this thing would never work. And as a human, you can say, I feel it work, so I just try it, even if there are few chances. While a deep learning algorithm will just tell you, no, you cannot do that. So to conclude, I will talk about 3 points. So the first point is that deep learning is for sure a huge step into artificial creativity. So before deep learning, there was no creativity in AI. And as we saw in the examples, we begin to have really very interesting applications in terms of creativity. Okay, so that's the first point. The second one is, as we said, disruptive creativity might not be reached by deep learning by design, because deep learning is based on optimization, and often disruptive creativity is based on face, actually, or feeling. So something subjective, where you say that you trust that something can work, but you have no proof of that. It's just a feeling that you have. And as it is not objective, it cannot be optimized. Okay, so a machine will never follow a face to do something because it's suboptimal. That's the second point. And the third point is that each time that we see creative applications working well, it involves both AI and humans. So I really think that AI and humans together is a real future for that. And that's an example here. In 2022, for the Modern Art Bucharest Biennale in Romania, they will use an AI called Chervis to be curator of the Biennale. So, of course, the curator, the AI will not be alone, but it will be able to suggest from different data sets from different museums, etc., to make suggestions, and then humans will do the choices. And this is really the future. Okay, so now I'll just let a few seconds on the references, so you see that there are a lot of links, a few papers for the creative applications, for the creative architectures, and about the creativity itself. There are quite interesting references in here. So as a takeaway message, we can say that humans are good in disruptive creativity and machines are good for optimization-based creativity. And this leads to the fact that humans and AI must work together to make good creative applications. And I will just let you with some seconds of sound of this collaborative way between AI and humans with the human robot.
Let me be music or a star into your mind. I'll clear this magic rules, 'cause I'm away for you by my side. My whole life, shades of delight, rich as a book before.